So nu det får screen var det. Jag har det här PowerPoint med engelska. Jag tror också för möjligt att jag ska presentera på engelska också. Vi kan försöka i alla fall. Eftersom jag har tidigare presentation med engelska. Men jag tror ni kan förstå det här. Betong med alkali-activerat slagg och nanoimpregnerat kolfibernät. Ja, det är min presentation. Är det inget problem, va?
Jag tar det på engelska. Det blir...
Okay, yes. Okay, so this presentation, I tried to address the questions about what is alkali-activated slag concrete, which factors affecting the strength and shrinkage, and also what is the general durability of alkali-activated slag concrete, and how is the acid resistance and temperature stability of concrete, and what is potential structures we can use for this alkali-activated slag concrete? What are the obstacles to application of alkali-activated concrete in the ordinary structures? And finally, I will present some studies to improve adherence between carbon fiber mesh and concrete. So this is my outline of presentation today. So first, we will look at the background. What is the alkali-activated slag concrete? So in fact, we know that we have a problem with this carbon footprint in production of Portland cement. Our concrete, we have to use Portland cement. Then that means that how to reduce the carbon footprint. This is our task in the near future. Then, in fact, alkali-activated materials, that is historically, even from 1930, we have already, in Germany, they have already started some alkali-activated slag. So you can see that in 50s, in previous Soviet Union, they studied a lot of systematically studied this alkali-activated slag. In France, in 80s, they studied some geopolymer. I think that is just a different mineral. When we use slag, that is alkali-activated slag. But when we use fly ash, that is geopolymer. So this is similar. In fact, it is also belongs to alkali-activated materials. In Sweden, in fact, our Chalmers first PhD student from building materials, it is alkali-activated slag by Thomas Tutti. I think this is Thomas Concrete Group's first manager of research and development. I think that all of you know him. He is now 75 years old. But he contributes very much to this alkali-activated slag. So during this, after 20,000, in fact, this become a very hot topic. So you can see that during after this 2000 year, so now we have already 3 books about alkali-activated cement and concrete, or alkali-activated materials, or even we have a handbook of alkali-activated cement, mortar, and concrete. So they and also there are a number of buildings, in fact, in previous in Russia or Ukraine and in China. In fact, they have already buildings, but not in Western countries so far. And in order to have this alkali-activated material, in fact, we have to use alkali-activator. So you can see that in the previous Glukhovsky, he mentioned these 6 types of alkali-activators. But in my opinion, in fact, the first one and the third one, in fact, that is very important for us. Because sodium hydroxide, that is quite easy to obtain industrially. And also sodium silicates, this is in fact water glass. That is also very easy to obtain from industrial production. So even in Sweden, we can buy it very cheap, I think. So this is why I focus on this third one, sodium silicate or water glass. I think that is also relatively low carbon footprint. But the problem is that first problem is that high shrinkage because of the low calcium silicate ratio. So this is the first problem. And the second problem is the setting time. But nowadays, I think that we can control the setting time quite good. So I think the second is not a problem, but the first one is still a problem. So this is the reason why we started a project from got the financial support from Vinnova in the past years. So this year we finished the project. This is why I want to present the results as a kind of implementation. So in this project, you can see Chalmers will respond. Chalmers is the leader of the project. We have the cooperators from Sverige, but now it is RISE, Secamp. And we have also a number of industrial partners in this project. Through the project, we found 3 very important parameters in proportioning of alkali-activated slag concretes. These factors include alkali content. That is basically sodium hydroxide content, and then silica content. We know that sodium oxide content, that is in fact basically try to increase the solubility of silicate. In our slag and also cement, we have a lot of silicate, silicon oxide. But the solubility of silicon oxide is very low, so we need the alkali to dissolve it. And then, of course, because this dissolution process is very slow, so we need to increase the earlier strength. In that case, we need to add silica content directly from water glass. So that is molecular level. So this is why we use water glass. And also, we found also very important parameter. It is gypsum content. We use gypsum to decrease the shrinkage, and also use gypsum to increase the calcium content. So this is the double reasons by using gypsum. So these 3 parameters we studied. So you can see that by considering sodium oxide in the left side, sodium oxides, you can see if we consider 4% to 6%, between this 4 and 6%, we can produce the concrete more or less like ordinary Portland cement. So here is ordinary Portland cement strength, compressive strength. So you can see 3 days, 7 days, and 28 days. It is in this range. So here, when we use, for instance, 5%, that is exactly follow 3 days, 7 days, and 28 days. Oh, this is 90 days. This is also in the range. So you can see this is sodium content, sodium alkali content, and on the other side, for silicon oxide content or silicate content. So you can see that if we have 6%, around 5% to 8%, so you can see that this is 1 day, but 3 days it is already here, 7 days, 28 days, and 19 days. So you can see that if we increase the silicate content, we can increase the early strength. So this is why we use both sodium content and silicate content to adjust our strength development. Then we also found very interesting relationship between this sodium content and silicate content, or gypsum contents. So you can see that this is 3 days strength. So we have a very good curve. We call it combined additions. So with a very good correlation. And this is 7 days, 28 days, 19 days, and even 1 year. 1 year's results. You can see that correlation is quite good. And then this correlation, we can express it by this equation, a combined addition. So we take sodium content as a 1, and then silicate content is 0.3, means that the contribution to the strength by silicate is about only 30% of alkali content. And gypsum is negative, 30% negative contribution to the strength. We know that gypsum has low strength, so so it negatively contributes to the strength, but positively contribute to the shrinkage reduction. I will show later on. So this is shrinkage. So you can see that this is ordinary Portland cement shrinkage. Here I compare only with the mortar. So I think the concrete is a similar tendency. So from the mortar, you can see that ordinary Portland cement after 1 year, it is around 1% or 1 per mil, 0.1%. Then for pure alkali-activated slag, it is about 5. You see here, 5 per mil. But if we add gypsum into this into the alkali-activated slag, so it will decrease the shrinkage. So if we add cement into the alkali-activated slag, so we will decrease the shrinkage even more. Here, this range, I think I have some picture here. So you can see that this is by adding gypsum. So this is by adding Portland cement. So we reduce the shrinkage. And if we consider both Portland cement and gypsum, we can significantly reduce the shrinkage from 5 per mil to 3 per mil in this range. So this is we do not need to consider, because this is in a very low Alkali-Activator. So the strength is low, so shrinkage is also low. but here the shrinkage, the strength is similar like Portland cement. But then we reduce the shrinkage from 5 per mil to 3 per mil. But to compare with Portland cement, we have about a factor of 3 to Portland cement. But for early strength, here we can see that we can almost for the early shrinkage about 10 days, we can almost reach similar level as ordinary Portland cement. So this is good for early shrinkage control. Then shrinkage also follow this combined addition effect. So you can see that we have also good correlation between these combined additions with the factor of combined additions. But the problem is that this factor will change with the age. So we summarized in this way. So you can see that this is shrinkage, and then this is sodium content, and then this is silicate content and gypsum content. So you can see that sodium negatively, sodium contributes to the shrinkage in this level, but silicates contributes even more to the shrinkage, much more than alkali. Then gypsum will expand. So gypsum will reduce the shrinkage by another way. So, but the most important thing is that it is only influence early age. So after hundreds of days, so you can see gypsum also already reduced their expansion. Then sodium and alkali also become more stable. So after about 200 days. So you can see that from here, we can see that sodium and silicate, they contribute to the shrinkage in a different way. So after our research, we suggest this proportion about alkali-activated binder. So about 80% slag, 20% cement, and then we have about 4 to 6% binder, 4 to 8% silicate. But this is water glass, so we can adjust the water glass in this level. Then we can use water band ratio about 0.4 to 0.6 so far. So this is if we use this proportion, we can see that we can dramatically decrease the carbon footprint for concrete production, and also keep the similar strength development. So this is the advantage of alkali-activated binder. Then what is the durability of alkali-activated concrete? So now I want to talk about general durability, which as we know that frost attack, chloride ingress, and carbonation. And I will also talk about acid resistance and high temperature stability. So this is different from ordinary Portland cement. So this is frost scaling. I think this Anders Linva, he helped me to do this experiment for scaling. So you can say this is a non-air entrained concrete. So the scaling quantity is about 1.5 to 2 kilo per square meter. But then I compared with our data from previously from our de-icing salts. I think the national project BTB Betong standards of Tersat Betong. So you can see that in fact, this alkali-activated concrete, the scaling, it is in the range of ordinary Portland cement without air entraining. So 0.4 to 0.5, you can see that it is in the similar range, even for the pure cement concrete. So in fact, it is not so bad. It is just similar. You can see. But then for chloride to increase, so you can see this is alkali-activated concrete. So this is ordinary Portland cement, and then this is slag 20%, 30%, 40%, 60% slag, and this is 20% flash. So you can see that this is 80% slag. You can see, but dramatically decrease compared with this 60% slag. So we can see that the chloride's increase resistance is much better by alkali-activated binder. For combination, this is the rice which help us to test it. This is this red point, that is alkali-activated concrete. So you can see that in fact we are in the middle. Of course, we cannot compare with the Portland cement. Portland cement, we know that any addition to the concrete by replacement by cement replacement materials, it will increase the carbonation. So you can see that this is flash, slag, and metakaolin, silica fume. So you can see the alkali-activated concrete, it is in the middle. So this is not kind of strange. I think the main reason is that we have lack of potentate, which is the buffer of combination, as usual. Then about acid resistance, so far there is no standards to test the acid resistance. So we tried to use this pH stat to keep the acids constant and then measure the weight loss. This is our first trial for the mortar specimen. So this is the result. You can see in the beginning we set pH 3 because I heard that from wastewater normally it is pH 3. So we tested with pH 3. Then we got this Portland cement without weight loss. So we found that the Portland cement surface contains so many white deposits. I believe that is gypsum. Then this gypsum will absorb water. So this is why we cannot measure the decrease of the weight. But when we decrease the pH to 2.5, then we got dramatic decrease of weight loss by Portland cement. The reason is that this lower pH dissolved this gypsum. So then we can say that in this case, all of this alkali-activated mortar, in fact, has less weight loss compared with Portland cement. Means that we have better resistance to acid. So this is for mortar specimen. Then later on, we considered this may not reflect the real situation. So we considered, so this is, you can see the results for mortar. This is Portland cement. So all of the alkali-activated mortar is lower weight loss. So, but the way in this way it is not so good. So we tried to test concrete. So by concrete, you can see we directly put lower. Based on our previous experience, we directly put pH 2.5. After 1 month, we found that the weight loss is not enough. It is just 1%. So we decreased the pH to 2. So after 1 month more, so means 2 months under this pH between 2 and 2.5. So we get this strength. We directly measure the strength. So you can see that after 2 months for alkali-activated concretes, so there are almost no strength loss. So that is keep the similar strength. But for ordinary concretes, the strength already decreased. So this is for high strength Portland cements. This is for low strength Portland cements. I got it from the literature. So you can see that for pH 2 to 2.5, alkali-activated concrete has very good resistance to acid. But afterwards, we decrease the pH to 1. That is very strong, 0.1 molar acid. So in this case, the strength become decreased. So this is you can see that the acid resistance is limited. It is only for pH 2 above. So if the pH is lower than 1, the concrete will become damaged. We cannot, but this is basic because our concrete is always alkali content, so we cannot really stand for acid. But anyway, for pH 2, that is good enough. For fire resistance, that is a little bit different. So you can see that, let me say, so this is Portland cement, 100% cement. So with 350, 550, and 800. So after 800, the residual strength for Portland cement is about 80. No, this is wrong. This is 350. Is about 80. But after 800, so the residual strength is about 30 for ordinary Portland cement. But for alkali-activated concrete, so you can see after 350, so the residual strength is higher than Portland cement. After 550 degree, the alkali-activated concrete is still higher than Portland cement. But after 800, so it is lower than Portland cement. So the reason is that after 800, in fact, everything in the cement, materials has been destroyed. CSH has been destroyed. But 550, that is only Portland cement, Portlandate, which is destroyed. But for alkali-activated concrete, we have less Portlandate. So this is why alkali-activated concrete has better stability to high temperature, up to 550. So no more. If it is higher than say 800, it is not good enough. And we also tested by Gullebu, AB company Gullebu. They are producing this safety chamber. So you can see that they tested our alkali-activated concrete. So you can see this is curve. Their requirement is that it should be 2 hours. It can hold 2 hours under 200 degree in the center of the specimen. So if it is this close, so you can see that if the concrete can keep 2 hours under 200 degree, so we think that is good enough for fire resistance. In this case, 2 hours, we have the chance to save our material. So this is according to their definition. So, but we tested two types of concretes. One is alkali-activated concretes, ordinary concretes with strength over than 50 megapascal, and another is lightweight concretes with vermiculate as an aggregate. So in this case, we got a very good curve. You can see that under 200 degrees, it is more than 3 hours. More than 3 hours. So that is good, very good for this fire stability. So in my opinion, if we combine these two concretes, so we will get very good fire resistance. So what is the potential applications for this type of concretes, alkali-activated concretes? In my opinion, for sewage pipe, surely we have the acids. It is about pH 3. So in that case, so this type of concrete should be very good resistance to the acids. And also, we can produce blocks and elements for infrastructures of wastewater purification. So you can see here, this is a type of wastewater which normally contain sulfate acids about pH 3. So for ordinary concrete, it will become corroded, damaged. But if we use alkali-activated concrete, I think that it can hold much longer time. So this is one of the potential application. Then another potential application is about this fire resistance walls or beams. If we can produce it as a kind of sandwich structure with strong concrete on the both sides, but with the fire resistance lightweight aggregates in the middle, then we can resist the fire up to 3 hours. So in that case, we have the chance to save our document. I heard that after 200 degrees, the document will become fired. So if we can have the time, 3 hours time to save, to transfer the document, then it should be good enough. So this is the second application. Then the third application, that is a little bit special. Recently, we had another project about this crushed concrete, recycled aggregates, very fine particles. We know that even for crushed aggregates, crushed rock, the fine powders less than 2 millimeter. That is very difficult to be used in the concrete. So how can we do it? If we use this alkali-activated concrete to improve this powder, we use this powder to produce different size of aggregates. You can see from 0.5 to 25 millimeter. Then we can produce the concrete with the similar quality. So this is what this is from our parallel project from Nhui Forsk, bottom ash for green aggregates. So from there you can see that for 2 days, 7 days, and 28 days, the strength is more or less similar, like reference. So here it is different bottom ashes, and with the produced by recycled aggregate, very fine recycled concrete aggregates powder. This is also just use slag with recycled concrete aggregates. So you can see that it is more or less similar. So we can use this technique to improve our aggregates in the concrete production. So that is also one way to reduce, to utilize the recycled material and reduce the footprint, carbon footprint. The obstacles obstacles technically, I think that we have 4 problems. One is about the large shrinkage, as I already mentioned, which is 3 times as much as ordinary Betong cements. And also the poor resistance to carbonation, but this is not this is similar like other materials, other supplementary cementary materials. Then air entraining, how to introduce the air. This is, I think I haven't looked at, and also super plasticizer. So this is 2. And mixtures, I think that's that need to be developed for alkali-activated slag concrete. For non-technical obstacles, that is national regulation and standardization. So this is a big problem in European countries. So you can see that in previous Russian, Soviet Union, they have already, even from '84, they have the standards about alkali-activated binder. Ukraine also has the standards in the beginning of '90, but for British standards institutes, they have also alkali-activated cementary materials. In China, they have also technical standards, but not in other European countries. So this is a problem. Now I want to take about a few minutes, about 10 minutes or 5 minutes about this carbon fiber mesh from China. So this is, I think, I asked Thomas Concrete Group why they do not use carbon fiber. So there, I think the big reason is that the bonding between carbon fiber and concrete is poor. So we cannot really utilize the carbon fiber. Then we develop a test to improve this bonding, so by nano impregnation. So after nano impregnation, I will show you this single pull-out test. You can see that after this pull-out test, you can see either the fiber become broken or pull out, but very difficultly pull out. So this is the curve. You can see this pull out. This is this red one is the ordinary fiber without treatment, without nano treatment. But all of this nano impregnated fiber, you can see that it shows much higher pull out strength and also a much longer displacement. So this is an indication of very good bonding. This one is the commercially a kind of SBR, a kind of rubber impregnated fiber. But our fiber is still nano carbon fiber is still much better than this one, than this commercial one. So so you can see that the pull out force is increased by 2 or 3 times. And then we tested the concrete by this nano impregnated carbon fiber to do a small test and large plates. And then this is the results. You can see that without fiber, the concrete just become broken as usual. With the fiber, original fiber without treatment impregnation. So you can see that after one one binding, so it become crank. But for the nano impregnated fiber, so you can see that the crank is just 0.1 millimeter, much finer than the non-impregnated one. Then the results you can see that this is reference broken strength, flexural strength, but this is without treatment by carbon fiber. After 3 binding, it becomes broken. This is nano impregnated fiber. After 11 binding, so it become broken. But the crank become 3.5 millimeter wide. So that means very strong, very high ductility. Then we tested the different fiber, different industrial fiber in this project, and then yeah, this is just the casting of the fiber, and then this is testing. We used our old three-point bending test. This is the results. You can see that for basalt fiber, after first and the fourth bending, so it become broken. This is a commercial rubber impregnated fiber. So also after fourth bending, it become broken. Then yeah, this is our non-impregnated carbon fiber. After fourth, become broken. And geopolymer impregnated also after fourth become broken. Then nano impregnated fiber without broken. So until 10th loading, it become broken. And then this is 7 days, but this is 28 days. Even after 15th loading without without broken, so it is still in whole. Here it is the result. You can see the curve. So it can deform even more. The strain can up to 6% strain, so quite high. And then we also tested this mesh in Alkali-activated Prism. So you can with the different position, we have the completely embedded, half embedded, and without embedded. Then we get the results. You can see that this is completely embedded after 15 loading with maximum loading. It is no damage. We cannot damage it. And then this is after 20th loading, so it becomes shear failure, shear crank. Of course this become broken because the fiber is outside. So yeah, so this is the curve. So you can see the crank after maximum loading, we have about 15 megapascal tensile strength, flexural strength. So the crank is just about 0.3 millimeter. So I think that is quite good. We did also large plates on the 4-point bending. So you can see this digital image correlation. So the cranks is very well distributed, and the plates become bending. I think about 5 centimeter. So you can see it is really bendable plates. This is the curve. So you can see that the force can keep up to 40 millimeter. Until 50 millimeter, it becomes broken. So we can see that the concrete, if we use this alkali-activated concrete, it can really keep the similar strength as ordinary concrete, but shows better resistance to chloride ingress and acid attack, and also better stability under the high temperature. So this is for alkali-activated concrete. For nano impregnated carbon fiber, we can see that it increased the bonding with concrete by a factor of 2 or 3 times. And the concrete reinforced by nano impregnated carbon fiber mesh reveals very good loading capacity with shear failure, very similar like oversized steel reinforcement. So it is possible to produce bendable concrete plates with nano impregnated carbon fiber mesh. So this is my presentation for all. I think a little bit late, about 50 let me say 50 minutes. Now we have 12 minutes for discussion.
Ja, men då tackar vi Tang för en trevlig presentation.